So in class today, we learned that the key to being able to analyze a rational function is to be able to simplify rational functions. And the key to simplifying is being able to factor. We are now working on factoring polynomials that look like this, a cubic polynomial. We're interested in finding out when does that polynomial equal 0, because if f of r equals 0, we know that x minus r is a factor of f of x. So the key to this whole process is finding zeros, because finding zeros is as good as finding a factor. We could just start testing numbers in here, throwing numbers at that polynomial, but we don't really want to do that, and we don't have enough time. We want to limit the set of numbers we're testing. So we build a set of potential rational zeros, and we do that by taking all the factors of 12, plus or minus 1, 2, 3, 4, 6, and 12, and writing it over all the factors of 1, plus or minus 1. Oh, look, it just stops at 1, which is your friend, because if you're writing fractions where these are all the possible numerators, there's only one possible denominator, which means we're not really going to have any fractions. So our potential rational zeros are 1, 2, 3, 4, 6, 12, and the negative sides of all of those numbers. Now that's 12 potential rational zeros, and that seems like a lot, but it's a heck of a lot smaller number than an infinite number. So now let's test this polynomial by taking a look at, using the coefficients 1, -1, -8, and 12. I want you to start by using the small positive potential rational zeros. So let's start with 1. We drop down 1, multiply by 1, that's what we're multiplying by, add them together to get 0, multiply by 1, 0, -8, multiply by 1, you get -8, and you get 4. That tells us that f of 1 is equal to 4, which is, makes us sad because we want it to equal 0. So let's move on to our next target. 1, -1, -8, and 12 stay the same. Drop down the 1 like always. Kick this up, and we get times 2, 2, 1. Multiply again by 2, you get 2, -6, and you add, multiply by 2, -12, add, and you get 0. Oh, that's great, because now we know that f of 2 is 0, which tells us that x minus 2 is a factor. What's even more special is that the other part that's left is right there. That means that we know that x minus 2 is a factor times something equals our original f of x, and that something is right there in the yellow. Because this right here is the constant, this is the x, and this is the x squared. 1x squared plus 1x minus 6. We're now in safe territory because we're in quadratic land, and it's nicely factorable on top of that. So you could write this as x minus 2, and in fact this next part factors into x plus 3 times x minus 2. And you could stop there. That is the fully factored form, or you could write it as f of x is x minus 2 squared times x plus 3. We've now factored what could be a numerator or a denominator. You also asked in class about, can this system, synthetic division, work with any polynomial, and it could, even quadratics, although it seems to be overkill and unnecessary. Here's what I mean. If I gave you a polynomial, or sorry, a rational function like this, in order to disvard this rational function, we need to factor both of these. Well, the factored form of the top, by guess and check, you can figure out, it might be 2x, 4x, you play around with it a little bit, and you might realize it's this. You can check to see if this works by multiplying it out, and it does work. Does that mesh, though, with what the potential rational zeros theorem tells us? Well, if we list all the potential rational zeros, 15 becomes plus or minus 1, 3, 5, or 15, which is not bad, but 8 is where the problem lies. We've hinted at this before. You end up with plus or minus 1, 2, 4, or 8. That turns your list of potential zeros into all of these pairs. There's the first 4, 1 over 1, 1 over 2, 1 over 4, and 1 over 8. But you can't stop there, because then you have 3 over 1, 3 over 2, 3 over 4, and 3 over 8. And you can't even stop there because then you have 5 over 1, 5 over 2, 5 over 4, 5 over 8. And then it keeps on getting better because it's 15 over 1, 15 over 2, 15 over 3, and 15 over 4. How many do you have there? Well, it's plus or minus. You end up with, there's 16 numbers in there, plus or minus. You get 32 potential rational zeros. Probably wouldn't be the best way to go about this, but let's just verify that this matches what we figured out up here. This factor tells us that the 0 would be negative 5 halves, and this tells us it would be negative 3/4. Are they both there? Well, 5 halves is, and plus or minus is, so negative 5 halves is. 3/4 is there, and so is negative 3/4, so we're all set. Does the math work? Well, 8x squared plus 26x plus 15. If we use synthetic division, our coefficients are 8, 26, and 15. Let's try negative 3/4. We should end up with 0 if we're lucky, or something went wrong. Drop down the 8. Now we multiply this 8 by negative 3/4, and you end up with negative 24 over 4, which is negative 6. You add these together, and you end up with 20. Now you have 20 times negative 3/4, which is negative 60 over 4, which is negative 15. Add them together, and you end up with 0. Now that does match. It tells us that this is a 0. But would you ever really want to test that whole list? No. So the best way to factor quadratics is still almost always, I can't really think of any time it wouldn't be, the best way to factor quadratics is going to be with guess and check. And are you always going to be able to factor quadratics nicely? No. You might need to use the quadratic formula. But just remember, potential rational zeros theorem works on all polynomials, but with quadratics, you're going to need to guess and check, and that just takes, in the immortal words of Allen Iverson, practice, practice, practice.